I think with that again, you're done with the pyrazolidinediones and the pyrazolones and the oxycam. So you're done with the enolics. Fortunately, I usually arrange these drugs such that the other two groups do not take too long. I start with the bigger groups so that we spend all the time on the bigger groups. These other ones take a little bit shorter. Any question up to there? We okay? Up to there? Any questions, class? If we do not have any questions, then we move on. And we move on. I think this was our last group, the selective COX inhibitors. Selective COX inhibitors. I think it's our last group. And after that, we look at paracetamol. We will be done with the non-steroidal, then anti-inflammatory. So we have looked all the other drugs apart from meloxicam. We have said it's a preferential inhibitor. Preferential inhibitor. Aspirin inhibitor, and we can explain why. The others are competitive, irreversible competitive inhibitors. But all of them will bind both COX-1 and COX-2. The degree to which they bind them is what is differing. One being completely irreversible for aspirin, the other one being reversible, and then the other one for the meloxicam being a bit more preferential for COX-2 than COX-1, but they bind to both enzymes. Now, as we had said earlier, there is need, because of the toxicity that was associated with these non-selective COX-1, COX-2 inhibitors, non-selective COX-1, COX-2 inhibitors, there was still need to further develop molecules that could go or which could selectively bind the COX-2. Remember, COX-2 is inducible. That is the inducible COX-2, and bind the inducible COX-2. Of course, in binding the inducible COX-2, they will also bind to, of course, we did mention that it's also constitutive COX, but they will leave the COX-1, and hence the toxicity will not. The gastric irritation, the imbalance in terms of homeostasis, in terms of the activity of the kidneys, and so on. At least that imbalance will not be to such a big extent, and that is the need. That's why there was need for selective COX-2 inhibitors, and the selective COX-2 inhibitors, the main category we look at here is the coxib. Call them the coxib. Remember, we did mention, if we are going to have selective COX-2 inhibitors, remembering that the COX-2 is the inducible enzyme, it is the inducible enzyme. It is being induced when you have inflammation, when you have an injury, you induce the COX-2. So, and we did mention that there is some a small structural difference between COX-2 and COX-1. Therefore, if you are going to get drugs that are selective for COX-2, you must also have some structural features within those drugs that allow them to select COX-2 instead of COX-1. And when we look at these drugs, we will see that they have structural features that allow these drugs to go for COX-2 and not COX-1. What are the features we have in COX-2? Remember, we did mention that because of the change of the enzyme, where in COX-1 you have isoleucine, in COX-2 you have valine. Then you find in valine there is a pocket. In valine, you do have a pocket, and that pocket, and in valine also, you do have, in valine, you also do have had a bigger hydrophobic area. So because of those structural differences between COX-2 and COX-1, you can make drugs that can go selectively and enter that pocket. So you make a drug with a rigid, we can say a rigid hand, like a hand. A rigid area, a rigid structure. It has a portion of it within itself which is rigid, and that portion goes for that pocket and enters that pocket, and therefore fits itself like a key and lock within that pocket. And once it fits within that pocket, then it will be able to bind that enzyme. And because the COX-1 does not have that pocket, then those drugs will not go for COX-1. So indeed, the development of the COX-2 selective inhibitors came about to match the structure. It actually was geared by the structural differences between COX-1 and COX-2, as we have already mentioned. So the traditional non-steroidal anti-inflammatories inhibit both COX-1 and COX-2 and thromboxane synthetase to varying degrees of selectivity. So they will, of course, also bind prostacyclin and also the thromboxane synthetase to varying degrees of selectivity. Decrease gastric mucosa, they will decrease gastric mucosal protection, resulting in ulceration that we have mentioned. They will also bring about stress-induced decreased renal perfusion, resulting in will also happen. Inhibition of thromboxane synthesis results in increased prostacyclin synthesis and reduction in platelet aggregation and increased bleeding tendency. Remember, inhibition of thromboxane results in increased prostacyclin synthesis. Remember, the thromboxane and prostaglandin and the prostacyclin, the thromboxane and the prostacyclin are supposed to be balanced so that you have a balance in the clotting activity, and you have also a balance in the bleeding. So there is so it is completely balanced, and that's what we called homeostasis. If you bring in a drug that binds the thromboxanes more, it means there will be lesser activity of the thromboxane. And therefore, remember, the thromboxanes are responsible for vasoconstriction and platelet aggregation, whereas the prostacyclins are responsible for vasodilation and reduced platelet aggregation. So if you bind the thromboxane enzyme too much, then there will be bleeding. If you bind the prostacyclin enzyme too much, there will be clotting. So these two have to be balanced. And we are saying that some of these drugs that actually were synthesized are selective COX-2 enzymes, unfortunately had a problem with the way they were binding the thromboxane. So inhibition of thromboxane synthesis results in increased this should be prostacyclin synthesis and a reduction and an increased bleeding. And that is actually what they were responsible for, because some of these drugs were also found to cause some blood disorders, and they indeed also did cause quite a lot of cardiovascular disorders, and they did cause some death. The non-steroidal anti-inflammatories with a greater selectivity for COX-1 generally causes greater GI bleeding and renal toxicity than those, of course, with greater selectivity for COX-2. That's just a summary of all that we have done. Selective COX-2, that one I think does not help us. And if you look at again your printout, I think those drugs, fortunately, are given the structures of the celecoxibs. Not celecoxib, the coxib. Celecoxib is one of them, sorry, of the coxibs. And I think we do have them somewhere. Coxib. Those are the piroxicam. Even phenylbutazone, oxybutazone is also on your structure, on your handout. Yes. Check page 17. If you have some of them, you might not have all of them. I think you have most of them. And then page 18 is showing their metabolism. Yes. So if you check your page 17 of the handout, they are called the coxibs. And if you see again, almost actually all of them end with a coxib. So we call them the coxibs. So there is the celecoxib, the lofecoxib, the lumeracoxib, parecoxib, valdecoxib, and the toricoxib. So if you look at these drugs, I hope you can see some structural similarity of these drugs with the pyrazolidine diones in form when you look at these two rings. There's quite some structured similarities, also structural similarities because of the presence of these two phenyl rings. Then when you look at these drugs, in all of them, you will see that they have, this is what I was calling the rigid structure. So you can see that group, you can see that group, you can see that group there, you can see that group there, that group, that group. The group could be either sulfamyl group, sulfamyl SO2NH2, or methyl sulfone group. So either methyl sulfone, for lumeracoxib, it is actually an acetic acid group. If you look at these drugs, this is what we are talking about, the rigidity. This is an area within almost all these drugs, which gives these drugs some rigidity. And because of this rigidity, this this portion of these molecules can go for that pocket that is found in COX-2. And since that pocket is not found in COX-1, they will selectively bind COX-2 and not COX-1. So if you look at them, that here is the 2 rings. And then if you look at this ring here, is with the rumidacoxib is a little bit different from the others. It has some structural similarity with the acetic acid non-steroidal anti-inflammatories. But if you look at all these others, you will see that the difference in them is the heterocyclic ring. That ring, that's a pyrazole ring, that's a furan ring, that is an isoxazole ring, also still an isoxazole ring, and then here you have the pyridine ring. So you can see, with the exception of the rumidacoxib, they have also structural similarities. And therefore, when we look at them, you see, we'll be mentioning that this ring, the ring to which the 2 benzene rings are attached, adjacent to each other, can have flexibility. You can have flexibility. Even the substituent on that heterocyclic ring also can have flexibility. But what is most important is that you do have, in almost all of them, you do have that heterocyclic ring attached in other position, in both its other position, attached to 2 phenyl rings. And on one of those phenyl rings, there is a rigid structure. So that is what we are seeing in all of them. If you look at parecoxib is actually a prodrug. It is a prodrug of valdecoxib. If you look at parecoxib and valdecoxib, structural similarity completely, this is a prodrug of this. So when this gets into the body, there is amide hydrolysis here. Amide hydrolysis of parecoxib is a prodrug of valdecoxib. So I think we just basically look, we are seeing some structural similarity. Incidentally, these drugs really do not have an acidic function because they are not really binding through the acidity. Their binding, as we have said, is a little bit different. Their binding and interaction with the receptor is not through mainly the cationic site, but they are going for the difference. And the difference between these 2 molecules is that one has a pocket and the other one doesn't. And the pocket is brought in by a slight difference in the amino acid, whether it is valine or isoleucine. So let us understand that these drugs might not really exhibit like the other drugs acidity, or might not really have an anionic center because their binding to these receptors is slightly different. They are taking advantage of the differences in these 2 enzymes. And since one enzyme has a pocket, they are able to go and squeeze themselves within that pocket and therefore bring selectivity and mainly bind the COX-2 enzyme selectively and not the COX-1 enzyme. So we can, again, that is a summary that we had mentioned, or is something we had mentioned. So we are saying selective COX-2 inhibitors were designed to take advantage of the much larger non-steroidal anti-inflammatory binding site on COX-2 compared to the non-steroidal anti-inflammatory binding site on COX-1. So that is a difference resulting from the substitution of the smaller amino acid valine in COX-2 for isoleucine at 523 in COX-1. That must be COX-1. Sorry about that. So there is a smaller smaller valine in COX-2, larger isoleucine in COX-1, creating space within COX-2 for binding of this drug. So the binding, the structural differences between these drugs and the other drugs we've been looking at can be well explained by the fact that these drugs are going for a different binding site as compared to the others that we had looked at. In COX-1, the larger isoleucine residue near the active site restricts access by larger, relatively rigid side chain substituents such as sulfamoyl or sulfonyl side chains usually seen in the selective COX-2. So that the isoleucine, which is a larger molecule, will not allow this rigid structure within these drugs, the COX-2 selective binders, to be able to interact or to be able to get or to interact with the enzyme, and therefore giving us very good selectivity. For the diaryl, so now you're looking at the SAR. For the diaryl, heterocyclic diaryl, you can see they have both rings. That's the phenyl rings. So for the diaryl heterocyclic compounds, the cis-tubine, I don't know whether I've drawn it. I believe I most probably have. Oh, I didn't. But when you talk about cis-tubine is when you look at the rofecoxib. When you look at rofecoxib, what you call the cis-tubine is where you have that phenyl ring and that phenyl ring, and then they are joined like this. See this double bond here. So the cis-tubine is that ring bond, and you go through that. Meaning cis means the big groups are on the same side. So if you look at this here, you can have this as a hydrogen and you can have that as a hydrogen. So you can either, because of the double bond, double bonds always create rigidity. That when you have that rigidity, you can either have the trans-tubine or the cis-tubine. The cis-tubine is where the two big groups are on the same side. Like you can see this and this are on the same side, and therefore the hydrogen and this other hydrogen, if you have if it's a cis-tubine, you remove this portion here. So this would be a hydrogen, that would be a hydrogen. So you find the hydrogens on the same side, and of course the big groups. That's what we're calling the cis-tubines. So for the best example is when we are looking at rofecoxib. So for diaryl heterocyclic compounds, the cis-tubine is in rofecoxib, the drug rofecoxib moiety, and the changes of one of the aryl rings play an important role in the COX-2 selectivity. So we are only saying that cis-tubine is important, and the changes that you have here, and it is para. If you look at this ring, and this substituent, it is substituted para position. So that change here, so the cis-tubine ring or this ring there is important, and also that para position substituent within that drug is very, very important. Celecoxib and paracoxib have sulfonamide substituents. So the cele and paracoxib have, you can still look at them in your, I have celecoxib and paracoxib. I have valdecoxib, celecoxib and celecoxib and paracoxib have sulfonamide substituent. They have an SO2NH position on one of the aryl rings, while etoricoxib and rofecoxib have the methyl sulfone. If you look at your structures, that is just direct. That you can see celecoxib has a sulfomoyl group. A sulfomoyl group is the SO2NH2. Rofecoxib has a methyl sulfone. Valdecoxib has also a sulfomoyl group. Those structures are the ones we are saying very important as rigid structures. Those are rigid structures, very important drugs. The oxidation state on the sulfur is important for selectivity. Sulfones and sulfonamides are selective for COX. Manipulate. All we are saying here is that heterocyclic ring, and that I did mention before, the heterocyclic ring, which is the five-membered heterocyclic ring that is joined to the two phenyl rings, and they are cis, they are on the same side, joined to the two phenyl rings, can be different. It can be manipulated. How? In celecoxib, we are saying it's a pyrazorine. Kindly look at that. You can write under your drug. That is a pyrazorine. In rofecoxib, it is a furan ring. In valdecoxib, it is an isoxazoline. So we are only saying that the heterocyclic, we have said with many drugs, that heterocyclic ring. In other words, you can have isosters. You can have isosteric replacement of one 5-membered heterocyclic ring with another ring, with another heterocyclic 5-membered heterocyclic ring with retention of activity. So that's all that point is saying, that you can have varying groups. You can have varying rings attached to the 2 phenyl rings with retention of activities. With that, so that does not change activities. Manipulated to include every imaginable heterocyclic ring and carboxylic skeleton of varying degrees. Carbocyclic, in that, if you look at one of those drugs which I said has a different structure than the others. If you look at this drug here, so this is the one, the numeracoxib. This is the rigid ring, but you can see it is joined. Of course, it's joined through a polar group, but you can see this one is an aryl ring. This is a carboxylic. This is not heterocyclic. It is heterocyclic when it has a heteroatom. But in rumiracoxib, which has structure with structural resemblance, a bit of it, of course, structural resemblance with the acetic acid derivatives, in that you have that phenyl ring there, and you have the acetic group there, joined with that, you can see, and then you have that. So in fact, it has a lot of structural resemblance with diclofenac. Actually has a lot of structural resemblance with diclofenac, because remember we say diclofenac has that acetic group there, it has an NH there, and but in diclofenac, that's a chloro group, that's a chloro group. So this borrows. So this drug borrows a lot from diclofenac, borrows a lot from diclofenac, but somehow it was found to be selective for COX-2. So that CH, so the group, the major difference here is that this drug has substitution on both rings. Remember, we did mention when we were looking at the other acetic acid derivatives, we did not have a substitution on this other ring. So this drug, incidentally, has substitution on both rings. Of course, this group and that group, again, throwing these 2 rings out of coplanarity and for maximum activity. So rumiracoxib is slightly different structure, but it's also demonstrating to us that the second ring, as calling this a second ring, can also be an aryl ring. It can be a carboxylic ring. In all the others, this, not the second ring, yeah, this ring. In all the others, this ring, sorry, the ring. So in rumiracoxib, this is this ring, which is the ring which carries a rigid group, is attached through a polar group to one aromatic ring, whereas in these other ones you have this ring attached to a separate. So in this one the difference is you have this separate ring here, but you can see the similarity because this group here is still attached to a nitrogen through that to that. So there is still a bit of similarity there, but a bit of course also a lot of difference. But the structure here, to be honest, the rumiracoxib has major structural difference when you compare to the others, because we are seeing, as I have said, it borrows more from the acetic acid derivatives than it actually borrows more from the phenyl acetic acid derivatives than it does from the other coxids. So we are saying that structure, that ring there, can be very different there. We can also have rigid structure attached to an aryl group. That ring they are different, that allows for quite a number of drugs. And that's the same thing that we are mentioning in the SAR, that the ring system that is fused in this tubing system has been extensively manipulated to include every imaginable, any ring, heterocyclic and carboxylic system of varying ring sizes. And therefore, we have said you can have the isoxazole, you can have the furan, you can have the pyrazole, you can have the phenyl, still with retention of activity. The amides, such as this group here, is found. I think this is what we find in paracoxib. That group, moiety, as in paracoxib, gave the prodrug. The prodrug for valdecoxib. Valdecoxib that statement doesn't make, there's something wrong there. So the imide such as that. So this gives us parecoxib, which is a prodrug. The parecoxib is the prodrug of valdecoxib. So that this group is found in parecoxib, which is a prodrug for valdecoxib. So parecoxib and valdecoxib share the same structure, with exception that, of course, if you look at this group here, this is the SA2NH. This is what is attached to the phenyl ring, and then of course it's an amide. You cleave here, you cleave the acetyl group, cleave it as it is an amide, and it gives you valdecoxib. I hope that is clear. Structural modification highlight the importance of binding to residue. They're only saying the structural modification in these drugs are only highlighting one thing: binding to the difference between these two enzymes. That's all we are doing. We are looking at the difference between COX-1 and COX-2 and taking advantage of that difference. This mutation appears to contribute to COX-2 selectivity by creating steric hydrons between the sulfonyl and the methyl group. So all we are saying is that once you have the isoleucine, it will not allow for these drugs to bind. There will be steric hydrons and the drugs cannot bind. That it is reasonable to expect COX-2 selective inhibitors to be more bulkier than non-selective non-steroidal anti-inflammatories. So we are only saying they are more bulkier because they want a lot of steric hydrons. They want to create a lot of steric hydrons between them and the isoleucine, but they go for the slim area whereby there is a space that is created for them. But when they approach the COX-1, the isoleucine, because of its bulkiness, introduces steric hydrons. There is steric hydrons between the isoleucine and the drug. Because of the rigidity, these drugs cannot bind COX-1, but they will go favorably for COX-2 and bind the receptor, because the COX-2 has lesser steric hydrons as compared to the COX-1. Might have gone on and on and on. What time were we finishing? What time did we start? At 11, eh? Did we start at 11? Class? Or we started past 11? Mnanyamazanga. Can we go on all? But we have done quite a lot today. We have looked at where did we start? We started at nabumeton. We went through, but these are, we went to oxycams. Then we have done the pyrazolones and the pyrazolidinediones. And now, actually, I didn't even expect that we'll be able to get to the coxibs, but we have. Are you saturated? Because once the mides are saturated, we cannot continue. Are you okay? Majiko Kamau saturation. Are we okay? All so, but we have done quite a lot today. Because we are just now going to go with the SAR for the different compounds. We don't have much because we need to finish these non-steroidals. You just the others, these ones are just mentioning these drugs, but actually have done most of it. As we finish with the SARs of the coxibs, even if I don't mention much about each drug, I usually mention each drug just to let you understand the differences mainly in the metabolism. The metabolism again is structure dependent, but again, if you look at those drugs, we have basically almost mentioned everything. So we will finish. You have just a bit of the SAR to do, and then we say something about each drug, mainly because, as I've said, of the metabolism, because the metabolism is structure dependent, and then we will be done. Wow. Selective COX-2 inhibitors, and once we are done with the selective COX-2 inhibitors, the only other drug I will look at in that class is paracetamol. So please read and understand the toxicity of paracetamol. Every drug given in reasonably high dosage or high concentration can be toxic. Kindly read about paracetamol and understand how it brings about toxicity, because that's what you finish off this and you look at the anilides. The main anilide, the most effective anilide is paracetamol, and with that we'll close. We will close on the non-steroidal anti-inflammatories so that we can move on to the antihistamines. It's also quite a big group. I think after this, when can we do? We can tell me now when we can do a fast cut. We can do a cut after now finishing the non-steroidals. It would be good for us to test our understanding of the non-steroidals. But I always give you an opportunity. And once we finish the antihistamines, then we can see whether we can do our second cut, hopefully. Is that agreeable, class students? Yeah, it's okay. We are stopping. I can see, yeah. I've also gotten exhausted. We also get exhausted. I've also gotten exhausted. So let us sign in, but I have not had any questions. So when I don't get questions, I want to believe we are all moving together. But I said you can always inbox me. You can always talk to me either on my phone or my email. Now all of you know my email because I send you the link. So you can talk to me where you have challenges. You feel you don't want them aired here. Just talk to me. Talk to me either through phone or through the email, and let us whatever you have not understood, let us discuss it. So Naomi, please discuss with the class. Let us know when we can do our fast cut.